This is Chapter 7. We're in Lesson 1, and we're going to talk about exploring exponential models today. The graph on the left is an exponential growth function, this one here. It's increasing from left to right, and the graph on the right is an example of exponential decay. It is decreasing on its domain from left to right. In our definitions, an exponential function is any function that can be written in the form of y equals ab to the x power. X is going to be a real number, and a is not 0, and b is greater than 0. Also, b cannot be equal to 1. So our base has to be greater than 0, and x is a real number. Exponential growth is anytime we have the function y equals ab to the x power. If the b value is greater than 1, then that's exponential growth. The growth factor is the value for b. So b is a growth factor if b is bigger than 1 in our standard form equation. So if b is greater than 1 in that equation, that standard form, y equals ab to the x power. Likewise, exponential decay is when we have our standard form ab to the x power, and the value of the base is a fraction between 0 and 1. Then b is that decay factor. And it's going to be that decay factor only if we're between a value of 0 and 1 in that standard form ab to the x power. And then we need to know that an asymptote is any line that a graph approaches, as x or y increases in absolute value, as x or y increases in its absolute value. And we'll explore that here in just a minute. So let's look at example 1. We want to graph y equals 2 to the x power. And we have a table here where we can evaluate that 2 to the negative 2 power is 1 over 2 to the positive 2, which is 1/4. 2 to the negative 1 power is 1 over positive 2. 2 to the 0 by definition is 1. 2 to the first power is 2. 2 squared is 4. And 2 cubed is 8. So when we graph these values are on our x and y table, we're going to see exponential growth. So when x is negative 2, y is 1/4. When x is negative 1, it's a half. 0, 1. 2 has 2, or 1 has 2, and then 2 has 4, and for 3 we have the value of 8. And if we did 4 squared is 16, so we would have a point up here. So here's our exponential growth. Y equals 2 to the x power. It's important to see that 0, 1 is a key point on our function. And if I switch colors here, our asymptote is the x-axis. So y equals 0 is our asymptote. And if we go back to look at that definition one more time, an asymptote is any line that a graph approaches as x or y increases in absolute value. So by that, I'm talking about if y increases by absolute value, you see as we go left, y is increasing in absolute value. So if we're way out here at 1,000, the asymptote is going to be at 0 based on 2 to the negative 1,000 power, would be a value very close to 0. Next, we want to use the characteristics of the exponential graphs to analyze. So looking at the domain, you can tell that the domain is all real numbers. The range on each one of these graphs goes from 0 to infinity, not including 0, but 0 to infinity. The asymptotes are going to be the x-axis, or y equals 0. And it's important to note that 0, 1 is the y-intercept. That's one of the key features of exponential growth or decay, and that there is no x-intercept. So those are important characteristics to recall. Next, we want to look at identifying exponential growth and decay based on our definitions. So if y equals 3 times 4 to the x power, you see that our base is 4. And if the base is a number larger than 1, that base, in this case, is 4. So this is an exponential growth function. And then what's the y-intercept? That would be when we substitute 0 for x. So our y-intercept in this case would be 0, 3. By substituting 0 for x, we have 3 times 1. In example B, the base here is 3/4. So with the base that's between 0 and 1, we have an exponential decay function. And our y-intercept, by substituting 0 for x, our y-intercept would occur at 0, 11. And then finally on the C portion, if you save $2,000 into a college savings account for 4 years, the account pays 6% interest annually. So this is a growth factor because we're growing by 6% each year. If you think about the base is your initial investment, that's your $2,000 plus a 6% growth, then your base is going to be 1.06. That tells us by definition our base is larger than 1. And the y-intercept is going to occur at 0, 2,000, since that was your initial amount. In fact, if you wanted, you could write the amount at any given time as 2,000 times 1.06 for that 6% growth raised to the power of time. So understanding our model equation, you want to know what each piece of the equation represents. And starting out with A of t, that's the amount that's in some account or some situation after t time periods. So that's the amount after some t time period. And our next bubble, that's going to be the rate, and it's going to be the rate of growth if r is bigger than 0, and it's going to be a rate of decay if r is less than 0. And this smaller lowercase a is our initial amount that you're investing or saving, or some bacteria. And the power t, that's the number of time periods. So anytime you see an equation in this format, you need to understand what each one of those portions of that equation means. So let's look at example 3, and we'll use that equation. Example 3 says, suppose you invest $5,000 or $500 in a savings account. So that's my lowercase a. The initial amount is $500. We're going to pay 3.5%. Moving that decimal over 2 places to the left, that would be 0.035. And we want to know how much will be in the account after 5 years. So our time period is going to be in years, and we're looking for 5. The general form of our equation that we're trying to duplicate is a times 1 plus r to the t power. So our general formula, a of t, lowercase a is our initial investment, that's 500, and we have 1 plus our rate of growth, and we got to the t power right here. So we want the a of 5 years. That means we need to go grab a calculator and substitute 5 up here for our time. And the a of 5 turns out to be about $593.84 if we've done our entry in the calculator the correct way. For example 4, if you invest your $500 in a savings account that pays 3.5%, when will the account contain at least $1,500? So we want to take that formula that we just created from example 3 and enter that into our calculator. And our question is, when is the amount going to reach $1,500? So I want to do two things. First, with our calculator, I want to graph the function itself. So you'll need to zoom out on your calculator to get the full feature. This is our a of t function, y equals a of t here. I've made my window go up to at least 2,000 on the y-axis. And then in red, I'm going to graph the y of t equals 1,500, which is going to be right down here. This is y equals 1,500. We're wanting that intersection point right there. So if you use that intersection feature on your calculator, you'll see at 31.935, the graph crosses 1,500. You can also use the table feature, and you would see on a table that between 31 years, which was $1,452.50, and then 32 years is $1,503.35. This is what you would see on your table. Then by the table feature, you know you're up to 32 years. So we could write a sentence that says, after 32 years, the account will contain $1,500, at least $1,500, since the interest is paid at the end of at the end of each year. So after 32 years, our account will have at least $1,500. And in our last example, we still need the calculator. The table below shows the world population of the Iberian lynx in 2003 and 2004. And I see that my source is not printed here on our notes. I got this information from the WWF global site that gives information about endangered species. So we want to write an equation. If the population is decreasing in an exponential manner and that trend continues, we want to know how many Iberian lynx will there be in the year 2014. And then I guess you could go check to see what actually happened in 2014. So here we have the model. We're going to write the model as y equals ab to the x power using our formula with the rate, 1 plus the rate. So the first thing we want to do is we want to find out the r value. So using the table, the r value can be found if we take 120 minus 150 and we subtract the year 150 divided by 150. Since I'm calling this my y1 and this my y2, and it says to divide by y1. So our rate is going to be Negative 30 divided by 150, so that turns out to be negative 2/10. The second thing we want to do is we want to find out the b value using this second formula. So this formula first, this formula second. Our b value is 1 plus the rate, and the rate we said was a decreasing rate at 2/10. So our base is going to be 0.8 or 80 in this case. The third thing we want to do is we want to write the equation. So writing the equation in our model formula would be y equals 150, that's our initial amount, times 0.8 to the x power. And if we want to know between 2014 and what was our last year, our first year was 2003. So that would be an 11-year time period. So our x value, this is what our x value is going to be. So again, with our calculator, want to be very careful. We get about 13 when we calculate that. So to finish up the question, if the current trend continues, only 13 Iberian links will remain in the world. And you may, again, like I said, you may want to go investigate in a search engine or look up the source, the WWF Global, to find out how many Iberian links are currently in the world. For me, today is December the 12th, 2021. So that's the end of our lesson. I'll see you in lesson 2.